I think this also answered the other question I had, because when we consider buckling, we're saying a deflection approaches infinity, but technically there's like when a column buckles,
Yes.
it doesn't, like, it's not like you have it going infinity.
Right.
Right. But it reaches a point that buckling has occurred on the way to infinity, even though it hasn't.
Correct. In fact, if we put all these together, right? And of course, let's consider stable buckling, because the unstable buckling is another issue. That means the structure will fail after buckling. In the post-buckling, it failed because of lack of strength, not fail because of deflection. So suppose we don't consider that. Suppose we consider stable post-buckling. That means the curve after buckling is going to go up, right? Something like this. That says nothing but in order to increase the deflection here, you need to increase the load. However, like the one I just made here, right? The one we talk about here, your deflection may not be able to go as large as you want. So there is actually another limit, which is somewhere here, right? There is your limit, and which is coming from subcompatibility. What does that mean? It's very simple. Just think about that if you have a building like here. In fact, this is the problem in the 1995 Kobe earthquake in Japan. They found lots of the building, they collapsed because of one building just impinged on adjacent buildings and consequently led to the collapse of the lower building. Why the building is shaking like this? And in that particular earthquake, the resonant frequency, which actually destroyed the apartments in the first, for the five-story and the 7-story apartments. That's the resonant or the key primary frequency in that particular loading. So as a result, apartments with a 5-story or the 6-story or 7-story, they shake significantly. And if you have buildings right next to it, they got damaged right here. Why? Because buildings are very close. Right? And as a structural engineer, what is your limit here? In this case, the limit is the gap, right? Between two buildings. So you cannot assume that I only consider my building, I don't consider the effect of the vibration of the building. Even in this case, we don't know which building is stronger, right? Even heating them.
You also want to consider the deflection of the other building, because you can't, because that's going to move this way and then this moves this way. So there's, but understood. Okay.
So in that worst case scenario, you know that this limit is definitely much, much less. Now, how do you predict what's this one? And that's the subject in structural dynamics. And in structural dynamics, we will analyze the time history and to check it. So this check is not, you cannot perform this kind of check in one calculation. Is more like you need to generate the time history response. You really have to know that, because in reality, the loading history is going to be like this, starting from some initial vibration, maybe something like that, right? Maybe during the earthquakes, it will actually be amplified when you have a resonant frequency like this. So you have to find out that not necessary to be the maximum or the positive maximum or the negative maximum, because the positive maximum only means that deflection is moving into one direction. So positive or negative is all relatively defined. That only means that if it's positive, I'm looking at building A. If it's negative, there's a building B. So your threshold here, you know that the maximum time here, the building is going to be here. This is for building B, and this is building A, right? And then you also have to perform the similar analysis for adjacent buildings, like the point you just made. Yes, they will not be standing still. They also will be moving. So you put this together and you see that when your building arrives at the maximum, which is closest to building A, what is the corresponding deflection of the building at a particular floor? And that kind of question can be answered by structural dynamics. Okay?
Sounds good. Thank you very much.
You're welcome.
Have a good night.
You too. Have a good night.